Even if they call you out.
But, you know, it goes back to Occam's razor, but, you know, how many hoops do you need to jump through to come up with an explanation?
Yeah, that's
I
the
mean,
whole thing.
The
like,
video I was watching,
that's how it started.
they were upset that the photos of the Earth were stitched together and edited. Is their nitpick number one. And the second one was he'd go into a salt bed out in Utah and do their experiments and he'd get the same results on the same location. So lack of diversity of location right there. And then they're also saying, well, if I watch a ship go out over the horizon, science is saying that's the curvature of the Earth, telling me that I can't see it anymore. But really, I can just get this other piece of equipment and see the bottom of it the entire way there. And then the physicist was like, well, if that was true, you could stay on the Empire State Building 1,000 miles away, see the lights of Chicago. You can go try that any day now, and I'll be waiting for the results.
Right, I mean, he's obviously
And they also say when
misled
Antarctica is
when
a
he
giant
says
wall,
that he could just get
the
the
line
piece of equipment.
Yeah, I've seen a couple of videos.
Shit,
No, like,
presumably. But I haven't tried. Could you explain
Thank goodness for the internet, so they can find each other. There was years ago dealing with snow, they were talking about, you know, what we call snow, it's not really snow. And they took a bullet towards the snow and you didn't get a puddle of water there. And see, therefore it's not, and then someone, of course, characteristically,
I swear to God, he died.
These people like
with manners,
He built his own
said,
rocket. He was
it's
aiming
called
to reach
sublimation.
5,000 feet.
Well, that and if it's a blowtorch.
And then at some point during it, he fell
Yeah,
out of
pretty
the
quick.
rocket.
And like.
at the beginning of the day, you wonder
People
why
think he
we're
was
debating about
unconscious
that, because
because
we're not getting
his
anywhere.
two backup
It's just an
shoes
argument that's
just
gonna never
into
end
his
or ever
main
fix
shoe, so he
it.
just
Ah.
hit the ground and died.
follower of the philosophy of Wittgenstein.
The video is crazy.
That which cannot actually be proven or disproven
Yeah, you
should
just
not
see a
actually
little
be discussed.
Yeah.
I think that is the most German name I've ever heard.
Yeah,
He was the practical philosopher. His background was civil engineering.
Because at the end of the day,
I don't like that.
you're gonna have your beliefs, they're gonna have their
Just like
their beliefs,
photographer.
nothing's gonna change, and you're
Never
gonna
try
go
to
about
stop
your life
yourself
and
from
continue what you did.
All right, so let's. Are there any questions before we pick up again on energy?
What kind of power you got? You got that solar power.
I don't want to.
Why can horses produce?
Why can't they?
Yeah.
Some say that any white question is actually a bullshit.
What's that?
It's one horse, they produce 15 horsepower. What?
That's an interesting video.
All right, so we last left off then with energy. We had the two types. We have potential and kinetic. There's rest energy also, but let's just concentrate on classical physics for the moment. So combined, it is mechanical energy. And the fact that mass is a form of energy shows up more at the end of second semester course. And so we generally write that energy is equal to kinetic plus potential. We had the three work energy relationships. The fact that the total work or net work is equal to the change in kinetic energy. This is also known as the work energy theorem. I would contend it's not really a theorem because kinetic energy and work are defined to make this happen. There's also that conservative work is equal to the negative change in potential, and that the non-conservative work is equal to the change in the total energy. I believe we got that far last time. I don't think we quite got to the ski slope problem. We did the object falling. How far? What was the last thing we did?
We did do object falling and then get an equation for potential energy.
Okay.
Yes.
All right, so if I take an object, oh, sorry, we left off with what were the infinite number of solutions for that?
Yes.
All right, so this starts out at, let's say, 10 meters above the ground, and I want to know how fast is it going if it falls when it is 2 meters above the ground. So this is a problem that you can use the chapter 2 stuff and solve easily enough, but I want to do it from an energy point of view. First, we need to establish that whether energy is conserved or not. And so, force diagram. What are the forces acting on it?
Gravitational force.
What else? There is no air resistance.
Well, at 10 meters? At 10 meters off the ground?
It starts 10 meters above the ground.
Okay, so.
Okay, so is this conservative or non-conservative?
Very conservative.
Conservative.
It's on the checklist, the easy way to do it. So energy is conserved. So I know energy initial equals energy final, which means kinetic energy initial plus potential initial is equal to kinetic final plus potential final. Here we go, I told you last time, we're gonna do this in unison. What's the formula for kinetic energy?
1/2 mv squared.
Not quite unison, but we're getting there. All right, so 1/2 mv initial squared plus, what's the formula for potential energy?
Well, it depends.
What was that?
It depends.
Okay. What is the formula for potential energy that is associated with weight?
MGH.
No, that's not necessarily unison thing. So MGH. Again, potential energy formula, there's one for every conservative force. 1/2 mv final squared plus mgh final. Now, if you're familiar enough with these, you can skip some of these steps, but I'm just going step by step. Not everyone has had physics before. Now we get to the point where we get to eliminate stuff. What is 0?
Depending on the coordinate system, we could determine, or we could, either the initial or final height could be 0.
What do you want?
Let's make the initial height 0.
Okay. Height is equal to 0 here, because Michael said so.
Wouldn't our velocity initially 0?
It would be.
Starts at.
All right, so that's 0 because the initial speed is 0. This is 0 because Michael says so. Now, don't forget, there is officially, there is some constant that we can always tack on to the end, but not necessary. We have 0 is equal to, well, actually, we can get rid of one other thing.
Oh, wouldn't, no.
Mass.
Yes. Steven?
Would it be easier to make the final 0, or does it matter?
It ultimately doesn't matter.
Good, because he said so.
I could be wrong, but I was just thinking, since you made the initial 0 at 10, wouldn't we be working in the negative for our final?
Yes, we would. And that's perfectly okay. Do recognize before, when we dealt with vectors, we were dealing with, we decided a positive and negative direction. When you're dealing with this, because the gravitational force is down, up is automatically positive. So if this is 0, this right here would be -8. You can't go say, hey, let's make down positive. That doesn't work here. And so we have 0 is equal to, mass cancels out, 1/2 times the final squared plus gh final. And so if we're solving for speed, v is equal to the square root of -2 gh final. Please don't just get rid of negative signs just because you feel like it. So this is the square root of -2 times, so in Earth, 9.8 times -8, which is the final height. If you don't like the negative height there, if you want to make the final height to be 0, the initial height becomes 8. So this term would have dropped out, this term would have stuck around. And so we end up with the square root of 12 point what?
52.
Meters per second.
And so from many points of view, a much longer way of doing it, but it does, the technique does become more convenient in just a moment. recognize, and this is the visual here, we start out, because of the way that where h was equal to 0 was defined, we start out with absolutely no energy at all. As it falls, my potential energy gets smaller, my kinetic energy gets larger, so that the sum always stays the same. So I can figure out halfway down my potential energy, well, it'd be half. It'd be the average between those two in this particular case. All right, I'm about to erase and do the ski slip problem. Thomas.
So was there any work done in this problem?
Yeah, the gravitational force did work.
So that is the work.
Yes, the work, if the question were, because remember, conservative work is equal to the negative change in potential, or in this case, since we assume that the weight is constant enough, the work done by the force of gravity is going to be equal to, well, my force of weight times the distance it went through in that direction, which would be 8 meters. So I'd actually have to give a mass to calculate that number. Let's make it 5 kilograms. So 5 times 9.8. See. 92 units.
Joules.
Yeah.
It would be joules. Newton meter is also acceptable. So that was the work done by the Earth. Did I answer your question, Thomas?
Yes.
Okay. Any other questions before I erase? All right, so let's take this whole idea and do the ski slope problem. You may draw your skier any way you wish. I like to think of this as Picasso-esque. So he starts out 50 meters up above whatever this is down here. He's sitting there in equilibrium. His initial velocity is so close to 0, it is good enough to count. So initial speed actually starts out at 0 meters per second. A gnat comes along and lands on his back, which is just enough to tip the balance. And so his initial velocity, we'll say, initial speed, we'll say, is close enough to 0 meters per second to count. He then starts down the slope. And so the question is, what is the speed at the bottom? So one of the things is, as he's going down here, the forces are varying. So let's just take a look at him when he's at this spot right here. So do the force diagram when he's at that point on the slope. What are the forces acting on?
Weight. We have normal force going at normal 2 feet.
That's it.
Okay, that's it. No tension, no other. All right, so we have two forces here. Weight, conservative or non-conservative? Normal force, conservative or non-conservative? You seem unsure. Someone with confidence.
Non-conservative.
There we go. You were right. Trust yourself. All right, so we have these two. We have a non-conservative force involved here. But the question is, what is the work done by each? Well, we know that there's going to be work done by the force due to gravity because he is changing in elevation. However, what is the work done by the normal force? Well, if you recall, work is The formal version of it is f dot dx or ds, dr, whatever letter you're using, from some initial position to final position. However, because the force is well, actually, no, we can do it like that. So, but the force is constantly changing, and therefore, actually, so is dx is constantly changing. Dx is always in the direction that he's moving at that moment. Dx is that way, normal force is that way. When he is here, dx is that way, normal force is that way. When he's here, dx is that way, normal force is that way.
So it doesn't matter because they're always perpendicular.
The dot product is 0 then. So the work done by the normal force is 0 because the normal force is perpendicular to the displacement while that force is involved. So therefore, the only force doing any work is a conservative force, therefore work is conserved. And we start exactly where we were before. Or we can start work non-conservative equals 0. Therefore, pardon?
I was gonna say work conservative equals a negative change in potential.
Yes. I'm going to start out with the work non-conservative though in this case. So work non-conservative is 0. So that means the change in kinetic energy is, try that again. Change in energy is 0, which means E final minus E initial is 0, which means E initial equals E final. I know it was a long way to get there, but again, I want to show that there's a connection between all this stuff. And if we had just jumped straight to this, I want you to recognize that this is implied in the background. So this is K initial plus U initial equals K final plus U final. Should look somewhat familiar. Here we go, another chance again. This time we have Austin, so Austin's going to chime in along with everyone else in unison. What's the formula for kinetic energy?
1/2 mc squared.
Okay, that was better. I like that. Some people were doing the rounds or the echo bit. See if we can. We'll get there. Initial squared plus. What's the formula for potential energy?
Depends.
Yes. Which one is also acceptable? In this particular case, what's the formula for potential?
MGH.
There we go. I put mass initial here. I'm assuming his mass has not changed. His body parts are not being left behind as he goes.
Well, skiing, that is a likely outcome.
All right, so now what can we get rid of?
We can get rid of
The first term,
the first term, yeah.
all the mass.
So it's stated that VI is close enough to 0, so that's 0.
Well, whatever H we said was 0, whatever the H final initial.
What are you doing?
Let's do H initial. Well, let's do H final. We did H initial last time.
All right, so H equals 0 because Nick said so.
And mass.
Don't worry, we will do a problem where mass matters, but not right now. So I have G HI is equal to 1/2 VF squared. This is very much like what we had before, but we have a different context here. So therefore, my final speed is equal to the square root of 2GH, which is square root of 2 times 9.8 times 50, which is 31 something?
31.304 or 05 meters per second.
Questions before I change the problem slightly? All right, He had so much fun, he decides to go back up to the top. He's standing there waiting for the gnat to land on his back to give him just enough of a push to start moving. In the meantime, he did not realize this, but there was a cave in. The gnat lands on his back and he starts skiing down. Don't worry, he is not hurt. At the bottom of the canyon right here, or the hole, are cotton balls, clouds, and kittens. Kittens were not landed on, they were there just for comfort. If it had been cats, he would have landed on them, and he would care. Who are the cat people in here? Before I got one? I think that was, in the opening orientation videos, I did comment that I insult cat. I maybe forgot. I did have one student who objected harshly to my treatment of cats and problems, but I had heard her complain about her cat so often I didn't buy it. If any of you have a cat and something bad happens to your cat, if you could just give me a heads up before I do some comment like that.
I'll just assume that you're the one who made the bad thing happen to the cat.
Okay. Through my psychic powers. All right, so anyway, he lands down here. How fast is he going just before he lands on the cotton balls and clouds?
The same.
Fast enough.
Or specifically,
31.305 meters per second.
because there's absolutely no difference in the problem here. And from an energy point of view, there is a vast difference between the two situations in the fact that the velocities are not the same, but their speeds are the same. Because in that particular case, we would go through the exact same steps, assuming Nick still picks the bottom to be 0. If he picked the top to be 0, we'd still end up with the same answer, just things would vary at some point around here. So, questions here before I change the problem slightly. As it turns out, the kittens led him to a door down here, and then there's a set of steps. He worked his way back up. While he was doing that, it snowed and it filled in the hole again. However, because this is a ski slope and this is what ski people do, at the bottom of here, they installed a giant spring with a spring constant of 50 newtons per meter. So let's talk a little bit about that. All right, so we have a coil right here. It has a certain natural length to it, and it does require force in order to extend it. As I pull on it, it will extend a certain amount. So the question is, how much force is required to stretch it a meter? Now, I don't actually have to stretch it a meter in order to figure that out. I could stretch it a half a meter, and that's half the force it takes to stretch it a full meter. And the amount of force it takes to stretch a full meter is half the force it takes to stretch it 2 meters. In other words, with a nice ideal, as this is an ideal spring, there's a direct relationship between the amount of force it takes to stretch it and how far you actually stretch it. They should be directly proportional. The slope of that is the spring constant. It's sort of a stiffness constant. The larger the number, the harder it is. The more force is required, the stiffer the spring is. So this is known as the spring constant. The force required, so this force is a conservative force, and I think that was on the list that we had before. So let's just go through a quick derivation here, and there's the eraser. Also, this delay is allowing more snow to fill in and pack so that he doesn't hurt himself. So I have a spring with some natural length right here. So this is where we consider equilibrium. This is where we establish our 0 point. The spring is basically moving from here to here. from some initial position to a final position. The work done by the spring as it stretches out is going to be equal to kx. Actually, negative kx, because the spring is always forcing back towards equilibrium, dot dx, from some initial position to final position. So we get negative, well, the force is that way that the spring exerts. My differential is that way, so they are in opposite directions. So we end up with, hold on a second, did I lose the minus sign in here? Oh. What should be? I'll keep it as x. They are in opposite directions, that's where the minus sign is coming from. So this becomes negative k integral of x initial to x final of x dx, which is negative k 1/2 x squared from x initial to x final, which is negative 1/2 k x final squared minus 1/2, I'm sorry, plus 1/2 k x initial squared. And since it's conservative work, that should be equal to the negative change in potential. So this should be the negative u sub f minus u sub I plus u sub I. Therefore, what is the formula for potential energy for an ideal spring? Or what is a formula?
1/2 kx squared.
Suppose I wanted another formula.
Plus C.
Yep. Kx squared. Now, oftentimes, instead of writing x, I'll write delta x, but ultimately, in this formula here, this is always, x is always from wherever the equilibrium position is, plus some constant if you wish, but we don't need that. We do need the mass in this situation, so let's make him sort of average mass, about 70 kilograms. I think that's US average. Questions before we get back to actually solving? Or let me state the problem. How much will the spring compress? All right, again, we now have, over the duration of the entire problem, we have 3 forces involved. Weight, normal, and the ideal spring. Normal force still not doing any work, and so what we're left with is the spring and weight doing the force, doing the work, and they're both conservative. So, dot, 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 E initial equals E final. K initial plus U initial equals K final plus U final. And once more into the reach. What's the formula for kinetic energy?
1/2 mv squared.
So I just like to bring it up the rear there. Although that was more in unison, thank you. In this particular case, let's just cut to the chase. In this particular case, what are the formulas for potential energy?
1/2. Well, mgh and 1/2 kx squared.
That's right. We have 2 different potential energy formulas here because we have 2 different conservative forces doing work. So I got 1/2 kx initial squared plus mgh initial equals that except for final. 1/2 mv final squared plus 1/2 kx final squared plus mgh final. And so now, what can we get rid of?
You can get rid of H final. Well, that whole term, yeah.
kx initial squared.
We assume that the spring is just sort of sitting there. Oh, sorry, that's wrong. 0 meters. Can't get rid of mass
Oh, yeah,
because
no,
we have a
yeah.
term without mass in it. There is one more thing that we can get rid of though.
Ooh, wait, V final squared. No. V final squared because it's when the spring is always all the way compressed in.
At maximum compression, it stops the person stops moving. So he starts out with all this gravitational potential energy. As he's skiing down, it's getting smaller and the kinetic energy is getting bigger. At the bottom, it's all kinetic and no potential. Then he hits the spring and that kinetic transfers back into potential. This time it's elastic potential. And so what we're left with here is the initial gravitational potential energy is equal to the final elastic potential energy. And so X final becomes the square root of 2mgh initial over K, which is the square root of 2 times 70 times 9.8 times 50 divided by 50 over there also. That's newtons per meter, that's meters. So the 50 cancels out, that's nice. That's 7, so it's roughly square root of 1400. So 10 square root of 14, so 34 meters.
37.
37? So that's how far this spring will compress before it shoots him back. When he gets shot back, how far up the cliff will how far up the slope will he go?
All the way back to the top.
Yep. And since his initial speed was not exactly 0, just close enough to 0 to count, he would actually then go off the other side. And how fast will he be going when he gets to the bottom down there?
31.305 meters.
If we did this same problem using Newton's laws, we would have to take into account, we'd have to know the formula for some math formula to describe the slope here, because the normal force is constantly changing as he's going